Thanks, Liang, for being here today to give the iQuiz seminar. Thanks, everyone, for coming. So Liang Jiang got his bachelor's degree from Caltech and PhD from Harvard before going back to Caltech as a postdoc. He then joined the faculty of Yale University in 2012, and then just last year in 2019, he moved to the faculty of the University of Chicago at the Pritzker School of Molecular Engineering. Today, Liang's going to tell us about quantum error correction for sensing and simulation. So go ahead and take it away. And also, sorry, please put your questions in the chat. And I think that Liang will break for questions after each section, maybe.
Okay, well, hi Elizabeth, and thanks for the invitation. And it's a great pleasure to have the opportunity to talk about kind of what we've been recently doing and using quantum error correction for sensing and simulation. And this is actually like mostly will be theoretical results. And this is in collaboration with the people from my former students from Yale and the colleagues from Yale and MIT collaborators and the people from Warsaw and Caltech. And probably like we all know, like error correction will be very useful for like different applications, ranging from like quantum computing, communication. Sorry, I just need to remove another screen. And the error correction and for communication, quantum metrology, simulation. And one of the major challenge for the quantum information processing, if you want to go to larger scale, is the decoherence. And for example, your qubit will be depolarized. And if you have excitations, it may be lost to the environment. And the system may be heated up by the thermal noise. So one question is that, okay, well, will error correction be useful for these applications? And I guess we probably heard many talks about, okay, error correction could be useful for computing, based on like fault-tolerant quantum computing ideas. And also error correction could also be useful for communication if you do some encoding or do some active error detection. And so today's talk, I'm going to be mostly focusing on the other two applications, namely the quantum metrology, if error correction could be useful for that. And also like a quantum simulation, if we could also use error correction to simulate some system while suppressing noise. So let me maybe start with the first part on this quantum metrology. And so one of the idea kind of like emerges around well, first the people have studied how to use error correction for quantum metrology for more than 2 decades. But it was kind of like a bit still vague that it's still, well, maybe one of the key questions is it easier or harder to use error correction for metrology as compared to use error correction for computing? And on one hand, we may say, okay, it's probably easier because okay, we don't need like a extreme like a precision, or we can average many times if we want to do the metrology. While on the other hand, if we say we do computing, we probably maybe need like a large scale and fault tolerance for computing. But it turns out that actually maybe there's some bit more interesting things that distinguishes error correction for computing and metrology. And I will talk a little bit about it. And so kind of what motivates me to think about quantum metrology with error correction was kind of 2 events happened in 2016. And one of the events is the detection of a first gravitational wave event, like by LIGO in 2016. And kind of that is kind of like a significant achievement of like a metrology. And there are also like various applications, like from larger scale to smaller scale, like MV magnetometer or atomic clocks. And on the other hand, in 2016, there's also like a breakthrough in quantum error correction, which is like in Rob Shirkoff's group that they achieved quantum error correction at the break-even using CAD codes. And also at the same time, there are also demonstration of error correction using trapped ions or MB centers or superconducting qubits, which probably mostly focusing on the error detection side around that time. So one question that naturally emerges is that can we actually use error correction to help quantum metrology? And to understand, first we will try to like formulate the kind of the general formalism of quantum metrology, and probably go through some simple examples to see that error correction sometimes can be useful to assist the sensing. Here, I mean useful is more like achieve like the Heisenberg scaling so that we can get the most from the quantum advantage. And then I try to develop a general criterion that under what situation that it's possible to use error correction to achieve Heisenberg scaling, even in the presence of decoherence. Okay, and then can explore like a different further extensions. So maybe one of the goals for quantum metrology is actually to estimate a parameter or multiple parameters that is characterized by the Hamiltonian of a quantum system. And here I'm focusing on a particular maybe specific case. Is the Hamiltonian doesn't depend on time, because that's the case we can kind of have well-defined like Heisenberg scaling, but there will also be other interesting cases. But here we're just focusing on parameter estimation of a time-independent Hamiltonian. For example, the energy difference between two levels. And the feature for this like quantum metrology is that the key idea is to use the coherent superposition of, if it's two level, you can do a 0, 1 superposition and let it evolve under the Hamiltonian. And then to accumulate a relative phase between the 0 and 1 state. And then one can use actually something called the Ramsey experiment to achieve the Heisenberg scaling. So I think that probably most people know about the Ramsey, but just to make sure like we're all on the same page, just the one slide for Ramsey, which is we have a two-level system starting a symmetric superposition of 0 and 1 state. Let it evolve under the Hamiltonian, which accumulate relative phase between 0 and 1. And then you measure what's the probability that the system still stays in the original state. And you'll find that actually there's an oscillation that depends on the waiting time and also the energy difference between the two levels. And if you have a total time t, then basically you can choose the measure, you can measure around the time, and you'll get a time sensitivity, a frequency sensitivity, which scales inversely with 1 over the measurement time t. So that's kind of the measurement sensitivity. And notice that it scales inversely with the total measurement time. And this is in contrast to the classical average, because classically, if we repeat the experiment many times, the number of repetitions scales linearly with n. And the uncertainty we get scales as 1 over square root of the number of repetitions for the classical averaging. So which scales as 1 over square root of time t, while in the quantum case, actually you get 1 over t. So this is actually indicating that if you have a pure quantum evolution, we can actually achieve Heisenberg scaling. And here, the Heisenberg scaling, I'm writing in the form of 1 over t versus 1 over square root of t for classical scaling. And there is a corresponding version. You can say it's 1 over kind of n, if you consider like a multiple sensors doing it at the same time, versus 1 over square root of n, if you consider repeating the experiment n times. So there's sort of like a 1-to-1 correspondence, which works for this time-independent Hamiltonian case. So now, if ideally we don't have decoherence, that works really nice. In practice, however, there are dephasing or the spin flips during these evolutions. Now, suppose you have dephasing, then the state evolution will not be a pure state anymore. So basically, after some like a measurement interrogation time for t, and then the evolution will evolve into a mixed state. So if you have dephasing, then off-diagonal entries will decay exponentially with this dephasing rate. And in the end, once you project to measure what's the probability over the initial state, then you will find that actually there is still an oscillatory pattern, but the prefactor for this oscillation will decrease exponentially with time, which means that it's probably not a good idea to wait for a time much longer than 1 over gamma. And so actually one of the optimum points is to choose the time to be of order 1 over gamma so that to optimize the sensitivity. So basically before the amplitude decays away, probably you should start doing the measurement. And then basically you have to restart the measurement and repeat the measurement like n times, which n scales as the capital T over T. And then it goes back to the classical averaging. So the sensitivity you get gets back to the 1 over square root of n, which scale as 1 over square root of t for the total time. So this again, that's usually that decoherence prevents us from achieving Heisenberg scaling.
Hey, Liang.
Yes.
Paul had a quick question that I think is relevant here.
Yes.
So he asked on your last slide, doesn't the quantum case still scale as 1 over square root of n? And and that you only get 1 over n if you have entangled quantum systems?
Yes, that's a great question. Yeah, thanks for asking. And first, like in the quantum case, if there's no decoherence, I will probably prepare a GHD state. Then that will enable to achieve 1 over n scaling. And and actually later on, I'll talk about that if you have multiple sensors, one can actually simulate such evolution with just a single probe, with the price that I have n times longer for the interrogation time. So that's sort of you can trade off, and basically what matters is n times t. That scaling, it will be either 1 over n times t or 1 over square root of n times t. Yeah, and hope that clarifies the question. Yeah, but here, just for simplicity, let's just focusing on the time, and which here we show the difference that if the decoherence, actually we might not be able to achieve the Heisenberg scaling. So one question is actually, is it still possible to restore Heisenberg scaling in the presence of decoherence? And well, I ask the question because there are some cases that actually it's possible to restore. But before we get to those cases, maybe let's first give a more clear definition about, well, what do I mean by decoherence? And so here actually I'm considering the most kind of the most detrimental decoherence, which is the Markovian noise. And which here the model, theoretical model, is considered as Concatenated equation with a Hamiltonian evolution and some quantum decoherence processes characterized by these jump operators, L1 up to LR. And so if it's a short evolution dt, then I can expand this dynamic equation and with the time or expand to the order dt. And you'll find that actually the evolution will mostly be like just the identity combined with some Hamiltonian evolution, combined with some like back action due to the decoherence. That kind of will be the dominant term. So when you take the dt goes to 0, it's just the identity, right? And then the decoherence actually induces some like a quantum jump processes characterized by these cross operators, which is proportional to the Lindbladian and the square root of dt to make sure the dimension is correct. Okay, so you can think that there is kind of a branching out, that there is some desired evolution and there's some like undesired quantum jump due to these decoherence processes. So this is kind of the noise model I'm considering. And I want to point out this is the Markovian noise, which is different from the kind of like the other noise models. It's time independent. Maybe we can use spin echo to remove the noise. But here we cannot use those tricks to overcome that. So we sort of have to use quantum error correction if it's applicable to suppress those noise. And now let's actually consider, okay, what do I mean by, how do we consider the metrology? And here we should, in order to understand how error correction could be helpful, we actually want to consider the most general metrological protocol. And here most general means that here I'm presenting a protocol which it actually can simulate all possible or other protocols. So here, let me just first describe the protocol and then I'll draw the connection to other protocols. So the protocol is called the sequential scheme. So the model is the following. It consists of the probe, which will couple to the Hamiltonian, which will like evolve under the Hamiltonian. And there is also an ancilla, which is some additional ideal system. Here I assume noiseless ancilla, for example, like if you have really long-lived nuclear spins, which can play the role of ancilla. And I have a combined probe ancilla system. I first prepare some like entangled or superposition state between the probe and ancilla as some encoding. Then I can use my probe to interact with the environment to acquire this parameters I want to sense. Then I can couple the probe with ancilla and then alternating this coupling to the environment, coupling to get the signal, and also this control between probe and ancilla. And this is what I mean by the sequential scheme. Notice there's just a single probe coupled to the kind of try to do the interrogation. And I assume noiseless ancilla. And ideally, I also assume there's a fast and accurate quantum control over the ancilla between the probe and ancilla. And the reason I notice that I agree that this is a very, very like ideal assumption because I assume sort of like a perfect probe ancilla coupling and infinitely fast. But the reason we make this assumption is because we want to know what's the fundamental limit that the error correction can help for our system. So here I basically don't, but later on I will try to see if it's possible to remove the ancilla and if there are other ways to relax these assumptions. But for the moment, I assume there's a perfect control and ultra fast control. Okay, just to see what's the fundamental thing one can do with error correction. And the one question kind of related to one scheme people might think, oh, what if I have n probes, right? And actually that scheme can be effectively simulated by using our sequential scheme. So suppose you have n probes, you can use n probes to simultaneously to interrogate and to get the signal, okay? However, the simultaneous interrogation can be reduced to our single probe acquisition if we can extend our sensing time by a factor of n. And therefore, we can essentially like a swap like between our probe and ancilla to effectively simulate that there is n probe which are simultaneously doing the sensing. So that scheme is called a parallel scheme, which can be actually reduced to our sequential scheme, because the sequential scheme, just at the price of extending the time by a factor of n, it can perfectly simulate this parallel scheme. So that's why we call this a sequential scheme is actually the most general one, which actually sort of captures all possible schemes that you may have. Okay, and here we actually want to bit more focused on kind of how to do these controls, and we'll consider just using quantum error correction to perform quantum error correction during these controls. And the goal is to remove the entropy from the noise and try to restore the coherence, and so that the probe there's combined with some ancilla, there will be some logical space, and there will be a coherent unitary evolution in that subspace. And if we could have some effective coherent unitary evolution in the logical space, then we might have some chance to restore Heisenberg scaling, because in that logical space, the system still behaves as a quantum system. So this is a bit abstract, so maybe let's look at some like examples. So the first example is actually a qubit probe with a spin flip along the x direction jumps. So basically Hamiltonian is Pauli Z Hamiltonian with frequency omega, and the dissipation is Pauli X. Okay, it's only Pauli X. It's not like a random rotation around different axes. It's only a random rotation around the X axis. And here the scheme, you can use a repetition code. Basically the probe is 0, you also attach ancilla being 0. And if the probe is 1, you attach the ancilla to be 1. So it's like a simple repetition code which spans a 2-dimensional subspace over a 4-dimensional space associated with the qubit and ancilla. And if there is a bit flip in our probe, then what happened is the 0, 1 will be flipped to 1, 0 for the probe and ancilla, and the 1, 1 will become 0, 1 for probe and ancilla. So therefore, you notice that if there's a bit flip, it goes to orthogonal subspace with respect to our logical space. So we can unambiguously detect there is a bit flip, because there's a simple procedure. You just measure the product of the Paulis of the probe and ancilla, and you will know whether it's +1 or -1. That tells you whether or not there's a bit flip happened while you're doing the interrogation. Okay, so if the bit flip happened, then you can undo the bit flip by applying X rotation on the probe. And if there is no bit flip error, then you don't do anything. You just let it keep continuing doing the acquisition. Okay, so now let's look at the procedure. So basically we start with the state that's encoded in the logical space associated with the C0 and C1. So after some interrogation for a small time dt, let's assume that, okay, the decoherence during that time, gamma dt, is actually much less than 1. Okay, so in that case, basically there are two possibilities. If there's no bit flip error, basically the system evolved as it should be with this desired Hamiltonian. And there's a little bit of reduction of probability because there's a finite probability there is no error. And if there's error happened, then the system evolved actually in this error space with C0 prime and C1 prime with a phasor, with also a phase accumulation, but it has a probability which is gamma dt. Okay, and as we said earlier, there is a way you can measure the product of the Paulis and to distinguish whether or not there's a bit flip. And if there is a bit flip, then basically you can flip back the probe qubit so that it restores back to the logical state. And after you're doing that, then basically to the linear order of dt, we basically have a unitary evolution within the logical space. And the error associated with the bit flip and the other contributions is only contributing to the second order of dt. Okay, so basically with this repetition code and this like a detection and correcting of bit flip errors, we're able to restore coherent unitary evolution within the logical space and accumulating the phase signal we want and suppressing the error to the second order of dt. And basically, we effectively achieve a unitary evolution within the logical space that with a Hamiltonian kind of edge probe tensor identity of the answer. And if we take the limit that dt go to 0, then basically we can neglect there is any contribution from the dt square, and we recover the effective unitary evolution within the logical space. And if we repeat this procedure many times, then we will effectively obtain a unitary evolution within the logical space. And as we mentioned earlier on, essentially we're doing a Ramsey experiment in the logical space that will achieve the Heisenberg scaling. So that's kind of the key idea, and showed in this example that actually for this particular case, when we try to sense the energy sigma z signal in the presence of poly X noise, we can actually achieve Heisenberg scaling assisted by quantum error correction with this repetition code. And this is actually like proposed earlier around 2014. And there's even an experiment using MV centers which try to demonstrate that there is some potential improvement with such a repetition code encoding. Okay, and on the other hand, there are also other cases that it may not work. For example, if you want to sense the energy difference between the two levels in the presence of dephasing error, then in this case, actually, there is no way to achieve this non-trivial unitary evolution in the logical space, because, for example, if we do the repetition code as we did earlier, 0, 0 or 1, 1, then actually we cannot detect or correct those dephasing error, because it cannot tell whether it's the dephasing don't change this logical space. On the other hand, if we do the repetition code with a plus plus and minus minus, then basically it will correct this dephasing error, but at the same time, it also corrects the signal as well, because the signal is treated as dephasing. So therefore, there is no way that the quantum error correction can distinguish whether the signal or whether it's a noise, because they essentially the same poly Z operator applied to it. So then the natural question is, under what condition error correction can help us to restore Heisenberg scaling in the presence of decoherence? Because obviously there are cases it may work, and there are cases it may not work. And so here is actually the general criterion that's actually obtained by my student Sisu Zhou, like around 2017. And basically, here is a statement of the criterion. And basically, your Hamiltonian will have a Hamiltonian operator, and the Markovian noise will also have the jump operators. And we can actually use error correction to restore the Heisenberg scaling if and only if this Hamiltonian operator is not fully contaminated by this Markovian noise. And the way you can interpret the Hamiltonian not contaminated by the Markovian noise, there is a rigorous statement is that the Markovian noise will span an operator space, which is called the Lindblad-Span, which consists of identity, linear or Hermitian conjugate of the Markovian noise, and their quadratic combinations. And those are, you can think as operator space, which are contaminated by the Markovian noise. And if by any chance your Hamiltonian has some component which is not in that operator span, then you will have some signal which can be distinguished from the noise. And even that's a tiny bit of signal, you can still use that signal to sense and for sensing. And because of that signal is sufficient distinguished from the noise, then you can use error correction to suppress all the noise and just keep that signal component and induce coherent unitary evolution within your logical space to achieve Heisenberg scaling. And so this is kind of like the underlying intuition of this like a Hamiltonian of this G operator is not in the Lindblad-Span, which is a necessary and sufficient condition allow us to achieve Heisenberg scaling with error correction. So now let's look at two examples we had earlier. So we mentioned that we want to sense the energy difference of a two-level system. So the Hamiltonian operator is poly sigma Z, and the dissipation operator is poly X. So the Lindblad-Span for this case is identity poly X. And you may have Pauli X square, but Pauli square is identity. So basically the Lindblad-Span is just identity and Pauli X. And in this case, actually our Hamiltonian operator, sigma z, is not in the Lindblad-Span because Pauli z cannot be written as a linear combination of identity and X. So therefore, we satisfy this condition. So there should be a Heisenberg limited version, which indeed, as mentioned earlier, we can use the repetition code to restore Heisenberg scaling for quantum error corrected sensing. Now, the other case, which if we have sigma z noise and we have sigma z Hamiltonian, then in this case, unfortunately, the Hamiltonian is within this Lindblad-Span because sigma z noise is can cover our Hamiltonian with a sigma z signal. So we cannot design an error correction scheme to achieve Heisenberg scaling. So maybe, I guess that maybe for the time's sake, in case people are interested, you're welcome to look into the paper. But here, just like a sketch of the idea, how we prove this condition. The necessity is actually proven by computing the upper bound of quantum Fisher information. So basically, if the Hamiltonian is in the Lindblad-Span, is in this contaminated subspace, then basically we can choose and compute the quantum Fisher information, which will be upper bounded by something linear with time t. And then we can use something called the Cramer bound, which says the uncertainty of the quantity you try to sense will be limited by kind of the inverse of the square root of the Fisher information. Then that will give you a bound which says the uncertainty will be kind of like a lower bounded by 1 over square root of t, which is no Heisenberg scaling. And the sufficient condition is proven by the construction of quantum error correcting code that can recover this unitary channel. And actually, there's an explicit construction of the error correcting code that we actually prove the sufficient condition. So I guess that maybe let me just go through one slide in case people are interested in this technical part, how we actually get the sufficient condition. And it's actually like not that hard. So the key idea is the following. We want to take advantage of this orthogonal component, the component of the Hamiltonian, which is orthogonal to the Lindblad-Span, which we call this G perpendicular. Okay, in this orthogonal component and of this Lindblad-Span, we can actually use that to construct the error correcting code. So first, the Hamiltonian can always be expanded in a linear combination of a component which is contaminated by the Lindblad-Span and a component which is orthogonal. And because identity is in the Lindblad-Span, so the orthogonal component must be trace 0, which means that you can write some parts which has positive trace, some parts which has a negative trace, and you can combine those two things to give you this orthogonal component of the Hamiltonian. And if we can call the positive trace could be called to be row 0 with the normalized version, and the negative part of the trace is row 1, which you can think those are two kind of density matrices. And those two density matrices actually need to have orthogonal support, and they actually corresponds to like two different like states which has no overlap. And you can construct purify those density matrices with additional ancilla, and that actually gives you the code word to encode the information that can be used for error corrected sensing. So one example, as we discussed earlier, if G perpendicular is sigma z for noise sigma x, then sigma z, you can write it as 0, 0, which is row 0, minus 1, 1, which is row 1. And you can purify it with additional ancilla. So basically the code word will be 0 probe, 0 ancilla. And the other code word will be 1 probe, 1 ancilla. And that's exactly the repetition code that we constructed and allow us to achieve Heisenberg scaling as shown earlier. So basically this gives you a generalized recipe, which actually invented by Sisi, that one can actually achieve explicit construct error correcting code that allow us to use quantum error correction to restore Heisenberg scaling if the Hamiltonian is not in the Lindblad-Span. So maybe just it probably could be more like intuitive to see some more examples. And here's the example which is kind of related to the earlier discussions of LIGO. That I'd say, okay, well, we're asking the question like, can we use quantum error correction to help LIGO to restore Heisenberg scaling? And so here we have the Hamiltonian, which is this, we want to sense the frequency shift of some resonator, which could be induced by the gravitational wave signal that induce the length change of the resonator and induce the frequency shift. At the same time, the system may have photon loss. So in this case, the loss is characterized by the annihilation operator A. So the Lindblad-Span, which consists of identity, these loss linear of these jump operators and the quadratic of those jump operators, it spans this operator space. And notice that the quadratic part of the span, which the A dagger A, is exactly the same as our Hamiltonian we want to sense. So in this case, unfortunately, the Hamiltonian falls within the Lindblad-Span. So basically, it's contaminated by the noise due to photon loss. So therefore, quantum error correction cannot restore Heisenberg scaling if we want to sense the frequency shift of the cavity in the presence of photon loss. And this is kind of like implying that, okay, there's no way to achieve Heisenberg scaling for LIGO in the presence of excitation loss. However, if you have a signal which is not just a frequency shift, if it's a Kerr effect, A dagger A square, then in this case, still suppose you have photon loss. The Lindblad-Span is spanned by this linear or quadratic combinations of A and A daggers. Then this Kerr effect is a quadic with A and A dagger. So it's not in this Lindblad-Span, which indicates that there should exist a good error correcting code to suppress photon loss errors while achieve Heisenberg scaling for sensing the Kerr effect. And it turns out it's possible. And one of the codes to do it is something called the binomial code, which was invented by my colleague Steve Gervin and a few others while we were trying to do error correction. And it turns out that code is also useful to sensing Kerr effect and suppressing photon loss. And intuitively, you can see it as a code word. The C0 is just a Fock state, which has a photon number n/2, assume n to be an even number. And the other code word is a symmetric superposition of a vacuum and the Fock state n. And notice that these two code words has equal average photon number, which enables it to actually have no back action from the photon loss to the first order. In addition, these two code words has a different variance of the photon numbers because for C0, there's no variance. For C1, the variance is order n square. And that enables us to be sensitive to the Kerr effect. So basically, this code word allows us to both simultaneously correcting photon loss while be sensitive to the Kerr effect. And that turns out that you can restore the Heisenberg scaling as calculated here. And actually, there are more code words that allow us to actually achieve the Heisenberg scaling for Kerr effect or higher order Kerr effect. And in case you're interested, you can look into this PIL paper, which gives the Chebyshev code and that allow you to systematically approach the best sensing limit. So maybe just as a summary and perspective for this part, which basically we can, the key condition, maybe the key take-home message is there's some operator space which contaminated by the noise, the Markovian noise, which is called the Lindblad-Span. And if your Hamiltonian is not in that Lindblad-Span, then you're lucky. You actually can do Heisenberg limited sensing with error correction. And there are maybe a few related further generalization to this question. One question is, can we optimize the error correcting code so that we can maximize our coefficient associated with the Heisenberg scaling? And the answer is yes. And we can actually maximize the design of the error correcting code by performing efficient calculation using semi-definite programming. And that allows us to come up with a good code word that optimizes the coefficient associated with the Heisenberg limited scaling. And second question is, can we encode without additional noiseless ancilla? Because that seems to be a very strong condition. And turns out it's actually possible, at least we have a sufficient condition. If the generator of the Hamiltonian is not in the Lindblad-Span, and also Hamiltonian commutes with the Lindblad-Span and the Lindblad-Spans commute with themselves, then there exists a quantum sensing code that do not need additional noiseless ancilla. So basically the error correction and the code space can already just using without additional ancilla, we can already do coding. And the third condition is in practice, however, this condition may not be perfectly satisfied. Maybe there is a small component of the jump operators that might cover or contaminate our Hamiltonian. But if that's really weak, then probably we can estimate the strength of those kind of small noisy part, which we might not be able to correct with our error correction. Then that gives us at least a boost improve the range of Heisenberg scaling up to a certain time scale, which is associated with the inverse of the strength of those jump operators. So it kind of guides the design that maybe one can design error correcting code to suppress the dominant part of the noise. And if there's a tiny bit of part which is just left behind, it's okay, because at least we can boost the performance up to the time scale, which is limited by the small part of the noise that we cannot correct with error correction. And if we want to sense multiple parameters, which is also a relevant situation in practice, is actually we can further generalize this condition. So if you look at this condition, we say Hamiltonian-Not-in-Lindblad-Span, which can be equivalently stated as the perpendicular part of the Hamiltonian with respect to the Lindblad-Span is not zero. Or mathematically, you can say another way is saying that the perpendicular part of the Hamiltonian is linearly independent. Here I just have one term. If it's not zero, it's not linearly like dependent, right? So then if I have multiple Hamiltonians, I want to multiple generators, I want to sense the coefficient associated with the generator of the Hamiltonian, then the generalized condition is that those perpendicular parts associated with the different generator of the Hamiltonian, they should be linearly independent. And it turns out that's a necessary and sufficient condition for multi-parameter sensing with Heisenberg scaling assisted by error correction. And moreover, we can further generalize this from the Markovian noise, which is this Lindblad master equation, to the general quantum processes characterized by the CPTP map. And in this case, these cross operators associated with the CPTP map, we can define effective Hamiltonian, which is associated with the kind of the derivative of these cross operators. And if this effective Hamiltonian is not in this cross span instead of Lindblad span, which is the span of the cross operators, then actually we can show that's a necessary sufficient condition for our Heisenberg scaling sensing assisted by error correction. So this is kind of, you can think it as a generalization to a more general quantum processes. So maybe just as a summary for the first part, is basically we develop like an optimized error correcting, we can further extend the results of Hamiltonian-Lindblad-Span by consider optimized code with noiseless ancilla beyond the Hamiltonian-Not-in-Lindblad-Span or multiple parameter or general quantum processes. So maybe the bigger picture is basically you can think that you have upper bound from quantum Fisher information, and you can also show some lower bound by explicitly constructing quantum error correction. And by further computing better upper bounds or design better error correcting codes, you can get to closer and get a tighter kind of probably like a design code that saturates this upper bound. Yeah.
So Liang?
So, yes.
Marius had a bunch of questions, but you seemed like you were on a roll. But would now be a good time?
Yeah, it's a good time. Yeah.
Hey, Marius, do you just want to unmute because you have several questions?
Yes, so I will just focus on the most important one. If you go back to page 42, I guess, 42 or 43, okay. You had a sufficient condition for, right. So do you really think that the commutativity of the Lindbladians here is necessary? I have the feeling that should not be necessary.
Yeah, it's probably not necessary, but here we can just only prove the sufficiency with this condition. And okay. I have the feeling, I think there might be other.
Yeah, I have the feeling if you have no extra Hamiltonian part in your Markov, then it should be okay. Then there should, you don't need the commutativity condition. That's what my perspective would suggest, but that's just a guess, of course. And then I have one question. This is probably at the beginning when you did this gamma t and dt, right? So so you're losing this probability gamma t. Is that not an issue? How can you renormalize this? I mean, mathematically, I can just divide by gamma t and then I'm fine. But can this then be done physically? This is always a mystery to me, how you can renormalize if you have lost probability.
So let me see if we if there is an example so are you referring to this slide? There is kind of a gamma
right,
t
exactly.
dt.
So if you look at this gamma t there, right, this is small. It has to be small.
It has to be small. By the way,
so you're somehow dividing by gamma t, and then this square should disappear if I'm not mistaken, but right?
Yes.
Because you're dividing by order t. But physically, how can you somehow ignore this factor because it's no longer a state, right?
Yes. So one intuitive way of thinking it is something kind of like a quantum Zeno effect. So if but here it's kind of like if you suppose like if you're looking at a state which you want to do a rotation from one from one state to the other, and if you keep measuring it, then basically the probability that it flip will scales as a square of dt, and if you keep measuring it, basically if and set the limit dt goes to 0, it actually vanishes. Or here maybe I can say another way is that suppose I cut this entire evolution by n steps, okay, and the probability of this dt square will go as 1 over n squared.
Oh, so
and
you're saying they have different
yeah.
scaling behavior, and that helps you.
That's right. Yeah.
Okay, good. And then just one extra comment. So you have this sequential model and the parallel model.
Yes.
But if you do the parallel model with the tensor product of the time evolution, you have larger code spaces which are completely left invariant, right? Because the tensor product always produces isn't that helpful? Because there you could use that to send some Hamiltonian or some, if you use these error unaffected spaces, is that not useful for your analysis?
I agree, it might be useful, but that can also be simulated with our sequential scheme. So you can think that you have a single probe combined with n-1 ancilla, which those n-1 ancilla actually stores this effective like n-1 probes. And so effectively your single probe and n-1 probe will be prepared in some like a permutation invariant space if we need that one. Yeah. So,
okay, so it comes from the simulation and you're losing the factor n, right? So
exactly, yes, and which is shown here. Yeah. Okay. So here I have this sensing time t, and over there it's a sensing time like t over n.
Okay. So the difference disappears in that analysis. Okay, thank you.
That's right. Yeah. Mm-hmm.
Thanks, Marius. Eric also had a question on the slide that you were sitting on at the end with the quantum Fisher information and the quantum error correction.
Yes.
And he was asking, how are you lowering the upper bound in that case?
So regarding the lowering upper bound, this is more kind of in the context of like a multi-parameter sensing. And if you have parameters, the tricky thing is that you may have operators which may not commute with each other. And for those sensing case, that actually quantum Fisher information bound is not tight. And you need to use this like a high level like Fisher information bound. So that will give you a tighter bound. And there are like it's more evolved in the calculation, but that actually can further improve. Yeah. But I agree, for single parameter, the quantum Fisher information bound it's there. Yeah. Okay. Right. So yeah, shall I move on to the next part? Yeah. So the next part is about this quantum. Let me move. About like a quantum simulation, and so one question is actually like probably people might heard about, like we can use the boson system to do boson sampling, which is actually, if ideally there's no loss, it might be very difficult to simulate and to get the statistics from classical computers. And so one question is that indeed the system have loss, and can we actually overcome the loss while preserving the bosonic nature so that we can do something like boson sampling or maybe simulating bosonic systems? And if you look at all the codings with the bosonic modes, actually most of the codings actually encode a D-level system or qubit or D-level system using bosonic codes. And this is kind of like a summary of the progress up to maybe 2018, like prepared by my former student, Victor Albert, when he was having a trip to Australia, giving a talk there. So you see lots of strange animals in Australia. But I guess the key idea here I want to show is that actually so far we do not have a code which can simultaneously correct loss errors while preserving the boson statistics. So the natural question is, can we encode a logical oscillator using multiple oscillators while correcting loss errors? Okay, so basically the goal is to construct some like lossless and preserving the bosonic statistics at the logical level. And actually there's a no-go theorem, that because this is a question which it's actually very natural and people have thought about it early on. And actually, like there is no-go theorem saying that if we just use beam splitters, squeezers, Hamiltonian detectors, you actually will not be able to achieve such a goal, because all those are Gaussian operations, which effectively can be achieved by something like a quadratic Hamiltonian or those evolutions that cannot correct loss errors. Okay, because the Gaussian operations kind of can, and there otherwise you will be able to get a kind of like improved like entanglement distillation using just Gaussian operations, but it's actually not possible in this case. So now we actually want to overcome this challenge of no-go theorem. And the way to do it is to change the conditions of the statement of a theorem. The condition is a Gaussian encoding will not work. And we try to do something which is non-Gaussian. So basically the idea consists of two steps. So first is that we want to convert the loss error into something called added thermal noise error, which is easier to handle. Second is that we want to introduce some non-Gaussian resource, which is called the Gottesman-Kitaev-Preskill state that can use to correct thermal noise errors. Okay, so in the next two slides, I will first explain how we convert loss to thermal noise. Second slide, I will define what the GKP state is. So first, how we convert from a loss error to thermal noise. So suppose I have a pure coherent state. I have a loss. Basically, there's attenuation in the amplitude of coherent state, but the amount of noise is still have this equal amount of uncertainty, because the coherent state in the loss still goes to a coherent state with a reduced amplitude. Now, what I can do is I can apply a phase insensitive amplification. Just to perform a two-mode squeezing over this mode and an ancillary mode which start in the vacuum. And that allows me to do amplification. So with amplification, you actually increase amplitude, but at the same time, you introduce some additional entanglement with this additional ancillary mode, which shows up here as there is a bit more uncertainty associated with this particular state. So basically, the pure loss combined with amplification actually gives you something effectively the same as the thermal noise added to the bosonic system. So now if we could develop a bosonic code that can correct this added thermal noise, then essentially we can actually correct the photon loss as well. Okay, so the logic is that if you have loss error, let's say I can amplify it, make it to thermal noise, and I can use the error correcting code to correct thermal noise, to correct loss error. Now, with that said, so basically from the rest of the discussion, I was just discussing how to suppress thermal noise. Okay, now in order to suppress thermal noise, there is actually a very interesting code called the Gottesman-Kitaev-Preskill code. And here I'm considering a particular case where the code space has just one dimension. It's just a single particular code state that actually defined as eigenstate of a certain operator. So first, we know that an uncertainty principle says that the commutator come from the commutation between position momentum is not equal to 0. It's actually a constant, I, h bar. And that indicates that it cannot simultaneously measure position and momentum to arbitrary position. However, you can actually do something, evade this constraint. Instead of measure position and momentum, you can actually measure position momentum modulo something. That's actually possible. So in order to show it, here, like one can first, from this commutation relation, you know that if you make a closed loop in the phase space, you actually will accumulate a geometric phase, which is proportional to the area in the phase space. And that mathematically, you can actually use the BCH formula to prove that you first make a displacement along P, then displacement on Q, and then make a closed loop. This product of these operators is actually a constant, which is proportional to the phase accumulation. And you can move some operators from one side to the other side. And if this area happens to be integer multiple of 2 pi, and here I say the area is equal to 2 pi, then basically it indicates that these two operators will commute with each other. So suppose I make a displacement along the P or Q quadratures, both by like a square root of 2 pi. Then those two displacement operators, they commute with each other. So if they commute with each other, it indicates it's possible to find a co-eigenstate of these two operators with eigenvalue, say +1. And turns out there is a one eigenstate which has eigenvalue +1 for both of these operators, which here we call the GKP state. And there is no information encoded here because it's just a particular state defined by the co-eigenstate of these two operators. And if you let it encode larger areas, say 4 pi or 8 pi, then you can encode multiple qubits using the GKP code. But here we just need a particular state, which is the co-eigen state of these two operators. Why I need that? Because first, it indicates that I can use this state to simultaneously measure SX and SZ, which allow us actually to simultaneously measure modulo Q modulo root 2 pi, or position modulo or momentum modulo root 2 pi. And this is actually allowed by quantum mechanics. If I remove the modulo square root 2 pi, then it's not allowed because I cannot simultaneously measure those. But if I put in this modulo square root 2 pi, actually these operators, they actually can be simultaneously measured. And that's actually useful because if you imagine you have some states like the GKP states in here, if there's some additional thermal noise being added, you can actually measure these quantities and know how much the thermal noise is added to the system. Okay, and here I introduce a particular, just as the trivial GKP states, because I'm not trying to do any logical computing. I just want to use it for sensing, to detect the thermal noise, which later on will help us to detect or suppress the photon loss errors in order to restore a bosonic modes at the logical level. So just give you some intuition about what GKP state look like. Here is a Wigner function of a GKP state, with horizontal axis being position, vertical axis being momentum. And you see a periodic structure of a square root of 2 pi, which is kind of consistent with this definition of a stabilizer, which is the translation. It's indicating the state should be translation invariant in position and momentum by square root of 2 pi. And this is this lattice structure. And I'll kind of put a Gaussian envelope on it so that at least I will not get a divergence in this expression. And here you can also, this is like a 3D plot of the GKP state with the Wigner functions. You see the positive, negative pattern. And on the side, you get the marginal probability distributions. You see there's a kind of like a spikes periodically spaced, that the periodicity is kind of exactly the square root of 2 pi. So because of these spikes are kind of like very narrow and periodically spaced, it indicates if there's small displacement, you will see the offsets in these spikes, and you can actually measure those quantities without destroying the whole state. So just to give you some idea, like so basically you can use this GKP state to measure the position modulo root 2 pi. So here is an example. Suppose I have a state. I want to measure position modulo square root of 2 pi. One way to do it is that I let this arbitrary bosonic states coming in. Let's do a control sum gate between the bosonic state and the GKP state. So control sum is achieved by this unitary, which is the exponential of a position of the first mode times the momentum of the second mode. And after this operation, you can think it as the position of the second mode being displaced by amount which is equal to the position of the first mode. Okay, while there's a back action, the momentum of the first mode being also shifted by something proportional to the momentum of the second mode. And that's allowed by unitary transformation. And then what you do is measure the position of the second mode. Because the position of the second mode is actually prepared in the GKP state, it has this periodic structure of modulo root 2 pi. So when I measure the position after this sum, I get the position of the first mode, which is modulo square root of 2 pi. Okay, so this is kind of the circuit to measure the position modulo square root 2 pi. Similarly, you can use a circuit to measure momentum modulo root 2 pi by using same GKP state. And by performing instead of control sum gate, you actually perform some like a difference gates. And following the similar mathematics, you can derive, like you actually can measure momentum modulo root 2 pi. So this is kind of explicitly showing you can perform sort of like a non-demolition measurement of position modulo root 2 pi and the momentum modulo root 2 pi using this additional non-Gaussian resource of a GKP state. Okay, so with this preparation, actually I can show the coding of this GKP repetition code. And this is actually invented by like a Ken Juno, who was also a former student in the group and recently joined Amazon AWS. So here the idea is basically you have an unknown state you want to protect. You let it couple and entangled with this GKP resource, non-Gaussian resource. Okay, now you get after this operation of control sum gate, you get entangled state between the mode that you want to predict, and the GKP ancilla. And then you perform some squeezing operations to massage the state so it looks better. And after that, you actually prepare the GKP repetition code. And now here I'm just going to illustrate how we actually use the GKP repetition code to correct errors. So the decoding procedure is the inverse of the encoding. Basically, if we squeeze along one quadrature, then you need to unsqueeze along that quadrature when you do decoding. And the control sum will be the control difference. And after that, you restore the state as it should be. So this is ideally, you just do the decoding like this. And in practice, there will be noise. So if there's noise, here I assume the noise model, which you have uncorrelated noise acting between this first mode and the second mode. So if you have noise added to the first mode, then what will happen is that those noise, one component will be passed on to the second mode. But it's okay because you actually measure this component on one component of noise in the P quadrature, and you can suppress that quadrature of the noise. On the other hand, the noise on the other component will actually be squeezed and suppressed by effect of lambda. So after this procedure, you'll find that both position and the momentum quadrature noise will be suppressed by effect of lambda. Because the one quadrature noise gets suppressed by squeezing, the other quadrature noise actually gets amplified by squeezing, but with the GKP ancilla, you can measure and suppress that quadrature noise. So basically, at the end, you get both quadrature noise get suppressed by effect of lambda. Okay, and the lambda is chosen to be effectively limited by this the finite squeezing of your the initial sort of like the magnitude of the noise that you added to the system. So you go noise from sigma to sigma square. And if you have noise added to this the second mode, a similar procedure can also be performed to suppress both quadrature noise. So here is kind of like numerically you can verify that here the noise, and that's input noise, and this is the noise after suppression. It has this quadratic scaling when you perform this GKP stabilizer code. So this is kind of like a summary of like you can have one ancilla mode, you can suppress noise to its second order. If you have two ancilla noise modes, you can suppress noise to its cubic order. And if you have n-1 ancilla modes, you can suppress noise to the nth order. So basically, there is a systematic way of designing the codes, which we call kind of the GKP stabilizer codes, because there is sort of a one-to-one mapping between the current coding using kind of a non-Gaussian resource of GKP state and the Gaussian unitaries of beam splitter and the squeezing. And that allows us to achieve the bosonic code that can suppress both position and momentum quadrature noise. And what's more important is actually in the logical space, we actually still preserve the bosonic nature of the system. So it is indeed a bosonic code for logical bosonic modes while correcting photon loss errors. So you can imagine that maybe these codes could be useful for like boson sampling at the logical level, or maybe you can use it if you want to simulate bosonic systems. And then these codes could give you a logical level bosonic encoding while correcting photon loss errors. And it can also be used for distributed sensing if you want to preserve some of the bosonic nature before you performing the sensing tasks. So I think that these are kind of like different applications one might consider. And just maybe as a summary, that basically like a key message I want to convey is that quantum error correction could be useful for various applications. Besides computing communication, it could also be useful for metrology as well as quantum simulations if needed. And finally, I would like to thank the people who actually work on these tasks besides collaborators. And I would like to highlight the two students like Sisu Zhou, who did a lot of work on this bosonic, the error correction with sensing, and Kenju No, who also did this bosonic quantum error correction while preserving bosonic nature. And yeah, thank you for your time. Yeah.
Thanks a lot, Liang, for an excellent talk. That was great. So do we have any more questions from people in addition to the ones that we had? So I guess I have maybe a very general question.
Yeah.
The result that you had that you couldn't do quantum error correction if the noise was within the or if the sensing Hamiltonian was within the subspace of the noise. That feels like a kind of a basic statement of sensing is about sensing your environment, and if the noise is in the same environment, quantum error correction is for being insensitive to your environment. And so you kind of maybe obviously can't quantum error correct the same thing that you can sense. Is that a reasonable interpretation of that result?
Yes, yes. In some sense, like once you understand the theorem, it's obvious, right? It's like you cannot distinguish a Hamiltonian from your noise, especially if the Hamiltonian if it's the same as the Markovian noise operator, like sigma z, then basically there is no way you can differentiate whether it's signal or noise. Yeah, and there could be a little bit non-trivial if you have photon loss and then you have a frequency shift. Then actually the quadratic part of this Lindbladian could also be contaminated, and that's the part which is a little bit less obvious. But on the other hand, you can think that if you consider the back action from the Lindblad noise, there is a term in your Hamiltonian which looks like kind of the k dagger k, right? And those actually will cause a decrease. It's a non-Hermitian evolution due to those parts, which you cannot distinguish whether it's a Hamiltonian evolution or whether it's a decoherence due to the Lindblad noise. Yeah.
Okay, thanks.
Can I ask a question just following that one? So is there a similar theorem where you would replace the Lindbladian by a fixed, the Krauss operators?
Mm-hmm. Yes, yes. And I think that's probably related to this statement. That's actually recently, Susu actually also worked out this general processes, which you can consider instead of Lindblad master equation evolution, we can consider general CPTP map, which characterized by these cross operators, which depend on the parameter you want to sense. And in this case, you can actually define an effective Hamiltonian, which is associated with the derivative of Lindblad and multiply its conjugate. Then you can show this is a Hermitian operator. And for this operator, if you want to sense, so if this operator, which is kind of, you can think it as it's an effective Hamiltonian associated with the omega. Okay, if that operator is in the cross span, then you will not be able to restore Heisenberg scaling. But if it's not, then you will be able to design a code to restore Heisenberg scaling.
Yeah, okay. I mean, of course, if there's no derivation in omega, then this might have to be tweaked a little bit, right?
Yeah. Yes.
If everything is deterministic, right, then you have to maybe change that a little bit. And yes, and that actually comes to my second question. So all this analysis is essentially for sufficiently small t, right?
Well, actually, for this general quantum process, it can be a finite evolution. It should work as well. But usually what happened is if you have Lindbladian dynamics, if you let it evolve for finite time, actually the cross operators would have higher orders of the Lindbladians.
Well,
and that's exactly part of the reason why if we start with the Lindblad master equation, we might need the dt to be infinitesimal small. However, if the general quantum process, somebody give you a black box, say this is a process characterized by these cross operators, then you might be able to, then you can just use this criterion.
Yeah, very interesting. Thanks.
I think Paul has a question.
Yeah, I do. Hi, Liang. So your notion of modular measurements, with respect to 2 pi, just reminds me a little bit. Yakira Harnoff always used to talk about modular momentum as a somehow a way of resolving lots of paradoxes or causing them. I don't know. He was, in his mind, those are kind of the same thing, I guess. Yeah. I'm just wondering, is this the same concept that he was talking about? Again, I haven't looked at his stuff in many years at this stage, but. Yeah.
Yes, I think it's related, and so I think that here I just listed one reference by GKP, which is the original paper that proposed the GKP code. And there are also like more recent papers by Barbara Tahar and others, which actually show that we can develop a scheme to measure these quantities. And also recent experiment by Michel Devereux's group, they're actually using a transmon. to kind of like to perform a weak measurement of this positional momentum modulo root 2 pi or root 4 pi. And you can actually, by just projecting those things, weakly measure it and adjust it. Following that, you can actually stabilize the system to a GKP logical space. So that actually prepare a logical state by this measurement and the feedback.
Interesting.
So it's actually a pretty powerful way of kind of prepare a state. You just keep measuring stabilizers and you actually prepare the state. Yeah.
Cool. Thank you.
Yeah, you're welcome.
Great. Well, thanks a lot, Liang, for an excellent talk again. And it seems like I think we're done with questions. So thank you. And yeah, you've got some